Good afternoon. We talked last time about the techniques used for access to memory by the processor and DMA that cannot be made at the same time. I presented you, we can say, classical approaches like hold cycle stealing and clock tick elongation with interleaving. Nowadays, we use much more advanced techniques, but they are mainly individual to systems proposed by the producers. For example, there is a solution similar to interleaving in Motorola, but based on fixed slots every memory cycle that has different clock from processor is divided, for example, into 3 time slots. For the processor, for DMA channel 1, for DMA channel 2. In every memory clock period, there are 3 slots. So this solution is synchronous, we can say. Another one is a solution with sub-buses. And we have dynamic allocation of processor and DMA channels to sub-buses that connect to given memory banks. We have separate banks of memory, which is typical in modern computers, not in laptops, but in stationary computers. We have typically multiple slots, and they form separate banks. And if DMA and processor use different banks, they can act in parallel on sub-buses. Another solution is dual-ported memory. Of course, it is much more expensive because dual-ported memory is much complicated from regular one. When we can have access by 2 ports, so we have fixed allocation to processor to 1 port and DMA to 2nd port, and they can act in parallel, provided they do not access the same memory cell. So there are modern solutions, but we don't explain in detail because they are specific to the producers, and there are many of such solutions. So I presented you 3 classical ones. Okay. How the access to device is organized programmatically. We have 3 types of access. It is interrupt-less access. It is interrupt-driven, but single byte or word access, and DMA. How it looks from program point of view. For example, when we send a sequence of characters to the printer. In every solution, maybe except IoT solutions, we copy data from user space to system space. Why? Please tell me why. You know that user space is another kind of system space, okay? This operating system has access to user data. So why we copy those data to system space? It's obvious. Because we have sweeping and swapping mechanisms, and data can disappear from memory. Because, for example, the page on which the data are located is freed for swapping purposes. So the data can disappear during the transmission. Because another part of operating system controls what happens to data in user space. Of course, we can build such a solution that we define pages that are used in given transmission. We can mark them sticky to memory, and they cannot be used in paging, for example. Of course, but I do not found such a solution. It's possible theoretically to keep data in user space. And for every character in the stream, which size is count, we check if the device is ready. Of course, it should be done with some timeout, and the system should react if the device is not ready for a long time. We leave those problems because this is the scheme of the driver. So we wait until, how we check the readiness of a device? How we check the readiness of the device? We read the status register of the device. How we do it? What instruction is used? In. Instruction in. Every device has a single data register and a number of control registers. And one of them is control register that holds the status of the device. When the device is ready, we send single byte or word to the device. How we do that? What instruction is used? Out. And we repeat it for every character. Finally, we return to the user. So two manners are used. First is that the user process incarnates to system process and does it on its own. And here we reincarnate to user process, or like in Phoenix, there is a limited process in IO server, and it gets the request from input queue of the server here, serves it, and sends a signal to the kernel to resume the user process that ordered this transmission. Okay. it is interrupt-driven programming. As always, we copy data from user to system space. From 0 to count, we check if the device is ready. Could it happen that between this and this instruction, the device stops to be ready? Is it possible? Of course. We pray that it does not happen. But sometimes it could be. We check the readiness, it is ready. We send a character, but the device is not ready. It can happen. What are the actions against this situation? Maybe repeating the transmission. But generally, we cannot avoid such situation. We pray that it happens extremely seldom. So we send a character to the device and we call the kernel. We suspend the process that operates on the device. Finally, when the entire string is sent to the printer, we do the same as before. Return to user. What does the interrupt handler? First, it tells the kernel, it's a kernel call, to resume the process that waits. So it's natural that there is additional variable here that the handler checks if someone is waiting for this interrupt. Because if not, for example, the user process resigned from sending more data, we ignore the interrupt. But it is model solution. So we resume the process. Waits. Which process? It must introduce itself. It must set some variable that defines which process waits for interrupt. And we resume just this process. Okay? But it is model solution. We acknowledge interrupt. It is hardware-based operation. Every interrupt controller needs to know when the interrupt service is finished. In Intel, it is write to port 40. In PC, not in Intel, in PC. Oh, in Intel, but the number of port is defined when the controller starts to operate. In PC, it is port 40. The data in this out is irrelevant. The write operation is valid. And the controller has internal stack of pending interrupt services. And this stack pops from the stack one interrupt. Okay? Do you understand what I'm saying? I believe that yes. If not, please tell me. Okay. And last operation is return from interrupt. What is it? Return from interrupt. It's IRET instruction that we learned. So, if operating system has no driver installed for given interrupt level, it has interrupt driver. Operating system has interrupt driver for every interrupt. So how to ignore the interrupt that has no handler? Those two operations, out to port that finishes interrupt and IRET, not more. However, it is not convenient to raise interrupt for every character, because you know that every interrupt causes context switch. That is very expensive. So we can optimize it and send only first character in the driver. So we copy data from user, we check for readiness of the device, we send first character P of 0, we set number of bytes transmitted to 1, and we wait for interrupt only once. In interrupt handler, if it's the last character, we resume the process. Otherwise, we send next character in interrupt handler. We send next character, we decrement count, increment number of character, acknowledge interrupt, and return from it. This optimization is, we can say, typical one, because it reduces number of interrupts that cause resuming of the process. Typically, we resume process only once per transmission, not for every character. And third, yes. If it is the last character, count is number of characters transmitted. If it's 0, we transmitted the entire string. Nothing to do. Resume the process. Otherwise, we send next character with index I. We decrement count and increment index for next transmission. How we start next transmission? Here we have out instruction. We talked about this previously. This symbolically shown as device, as variable, assign the vector element. Okay, let us interpret it in assembly language. Interrupt handler. Call. It's not system call, it's internal call in operating system. So it is not executed by software interrupt. It's call kernel. Or maybe, okay, if. Oh, only this part. only this part, okay? Because this is done in, yes, it's okay. I don't know how to write conditional jump, so I will use PDP like mnemonic. So count, jump, if 0 A in assembly language. Call kernel resume. Oh, here we should appoint which process. We should set the variable which process to resume. So push waiting process ID, call kernel, and jump to B. Label A, load P, load P, no, we must modify by I. Oh, I will write symbolically, load P of I. We should use indexed addressing here. Out data port. Oh, accumulator. When we do not specify number of registers, it's accumulator register. And decrement. Count, increment I, label B, out port 40, anything, and IRET. Okay? Is it understood? Not? So the problem should lay deeper than we are talking about. Could you specify what do you not understand? Oh, if else is organized as number of jumps in assembly language, okay? Not, but because here we out a character. So for this out, next interrupt will come. For every out, the interrupts responds with interrupts when the data is transferred. This is first out, and every next is done in this else phrase. Okay. And this is DMA based operation. It is extremely simple because we just copy data from user space, we set up DMA controller, and we wait for a single interrupt. Setting DMA controller is sending to the controller address in memory, address on disk, length of transmission, and direction, read or write. And wait for interrupt. Interrupt handler, acknowledge interrupt, resume process, return from interrupt. So it's extremely simple. Of course, real handler has exception handling for enormous number of possible errors. We just show the scheme, the model of the driver. Typically, we have several drivers that add new virtual features to the device and hide some specific features of the device. The topmost driver, we can say that file system is on the top of this stack that operates on symbolic data. So here we have the operation on physical device. Here we have some new features like optimization, like virtual addresses. So we have more advanced driving and file system on the top. And every call comes through all those levels. Here is the order for the transmission in physical driver, like that. Device works and answers by interrupt, which wakes up microkernel. Microkernel directs the interrupt to this point. Okay. Here we have the view of mechanical disk. Nowadays, in our computers, we use electronic disks, but still, the mechanical disks are of more capacity, and they are much cheaper per bit than electronic disks, so we still use such mechanical disks. How is built? There is a number of plates that rotate on common axis. And we have a mechanism of moving heads that move over the surface of those plates. So they are nearer or farther from the axis with step motor. So given position that is stable of this step motor gives access to the data distance of given distance from the axis. And those data on a single plate are called a track. The track is organized such a way that special combination of data appoints start of the track. And from the start of the track, we have sectors that are preceded by some headers, ended by the trailers, and the data inside is some amount of data, which is, of course, power of 2. Okay? All the tracks distant from the axis of given distance are called a cylinder. The cylinder is virtual entity. It's a collection of tracks distant of given distance from the axis. Okay. So the level of access to the disk could be specified, for example, such a way. On 0 level, we have hardware. It is the physical disk with the operations like move heads, activate heads, deactivate heads, and read a sector or write a sector. On level 1, we forget about heads, about a motor that moves the heads. We have just a package of data indexed by cylinder number, in cylinder head number, because every plate has 2 surfaces, up and down. So even if we have a single plate, we have 2 heads, and sector number. On higher level, we do not look into physical address. For example, it's typical that number of sectors on the track is not power of 2. It's as many as we are able to write with maximum density. So there are some addresses, some sector numbers that are not physically represented. For example, if we have 18 sectors per track, we need 5 bytes to address them. But the addresses like 20, 30 are not represented physically. So we have gaps in address space. But the handler on this level gives us continuous space of sectors from number 0 to maximum number. It fixes the gap by some mapping, the gaps in track number. Number of heads. If we have, for example, 3 plates, number of heads is 6, it's not a power of 2. So we must make some mapping. By the way, modern disks do the mapping themselves. They do not present us the actual number of cylinders, heads, sectors per track. They lie simply. So in modern disks, only number of cylinders would be not power of 2. All others are reported as power of 2, which is not actual. But of course, if we take elder disk, we will have such mapping that must be made because they do not report for every number the scope that is power of 2. So this is needed to have smooth addressing. and continuous addressing. Okay. Over this, of course, when we write or read from the disk, we must specify number of sector, number of cylinder. But we can divide the disk into partitions, you know it, up to 4 partitions per disk. And in every partition, we start addressing from 0. And we arrange higher units of information than sector. The disk is divided into allocation units. Of course, it is power of 2. And it can differ from partition to partition. Partition 1 has 4 sector units. Partition 2 has 2 sector units. On highest level, it was not in Windows. Maybe now they organize it, but it is typical in other operating systems like Linux, for example. We can merge several partitions on separate disks to a single logical disk. On this level, those disks can be even disks of different interface standard. We can take one SAS disks and one what's the name of, not IDE, but SATA. And we can join them to one logical disk, because this level driver knows if the address is in first scope, the transmission is on disk 1, otherwise it's on disk 2. And we can build such a stack of logical drivers that add some virtual properties. The abstraction grows upwards. And these are typical operations. Move head to cylinder with given number, activate the head. It is set of operations on lowest level. Here we have read or write sector with coordinates 1, 0, 2. Once cylinder 1, head 0, sector 2. Here we have read or write sector number 7 on the disk. But here we have partition number and allocation unit number. So partition 2, unit 4, which is transformed to number of sector on the disk. And finally, on this level, we have logical disk 2, unit 5. And if unit 5 is on this disk, the driver for disk 1, physical disk 1 is called, otherwise on physical disk 2. This shows how the stack of drivers can be built in operating system. On some levels, typically on higher levels of drivers, some optimization can be established for access to the device. I will show it on an example of the disk, which is most common massive memory device. In electronic disk, we can specify arbitrary arbitrary address, and the transmission time is irrelevant on the position in memory, in this memory, because it's electronic. But on physical disks, we can optimize, but what we can optimize? If there is no request, the disk just spins, we cannot optimize anything. If we have a transmission that is being executed, we cannot optimize anything. We must finish this transmission. Even if we have a request pending, we must finish current transmission to switch to the next one, because the disk realizes only one transmission at a time. Only if we have more than one request while we are transmitting data, we can choose which one will be the next, the left one or the right one. Okay, so if we can optimize if we have a choice. Okay, so let us observe several optimization techniques. They are called algorithms, but we know what is algorithm. They are techniques, not algorithms. Just like in memory allocation, first fit, best fit, worst fit, there are no algorithms. There are rules or techniques for memory allocation. The orders are specified by blue arrows, and the schedule is shown in black numbers. Head position is shown by red arrow, and execution schedule is shown in red. So let us look at, it is not optimization. It is basic scheduling of operations, FIFO. It means the transmissions are realized in order they come to the driver. So if the orders come in the order 1, 2, 3, 4, they are executed in the same order when current transmission finishes. First optimization is SSTF, shortest seek time first. The name says everything. Nearest to current head position, to current cylinder, of course, is cylinder with order number 3. It is realized first because it's closest. From this position, we skip to this one, from this to this one, from this to this one. It is the most optimizing algorithm. However, the middle of the disk is preferred. The head seldom comes to transmissions at ends. So it's fastest, but not fair. More fair is scan algorithm or technique. It's similar to the elevator. Not exactly. Every book says that it is near to operation of a lift, but we know that if the cabin goes up and we will press an order button to go down, and there is a higher order, the elevator will not stop at our level. So it's different. But general rule is that it has a direction. So we have current direction that can change. If current direction is to the left, it's to lower cylinder numbers. We realize the nearest transmission in current direction. So this is first, this is second. Here the head changes the direction because it's last to the lower addresses, and we realize 3 and 4. It's more fair, but still the middle of the disk is preferred because we realize the transmissions in both directions. If we go left or right, middle of the disk is served. And the last, which is most fair, but optimizes less than others, is cyclic scan. We have a fixed direction. I recall a joke on Dilbert. Do you know Dilbert? There are comics made by Scott Adams in some newspaper about a worker in some company. He calls the help desk and says, "How can I move the mouse pointer to the right? Because I reached the end of my desk and the pointer is still not at the rightmost position." And they tell him, "Please move your desk towards the wall." So here, what is if we reach the end of the disk? We do not move the desk on which the disk is working, because we assume that the lowest and highest cylinder number stick one to another. So after cylinder number 0 is cylinder number maximum. So we make a circle in cylinder numbers. So when the direction is fixed, always to the left, or maybe always to the right, and if we finish this transmission, we move in this direction. So it will be realized that this one, then we go to the left, and this is more to the left, and realize this one, then this one. So we need not move the desk. There are quite funny comics by Scott Adams on IT engineers. There in the comics there is IT engineer called Alice, and she gives funny for us hints for the workers. I must find this comics to illustrate our optimization technique. Okay, let's talk about write. right, is redundant array of independent disks, not always independent. Logically, in every solution, they are dependent because we split data between, so they depend on each other. However, physically, they can be more or less independent. I will describe this. Okay. It's a technique for creating virtual disks that have more space and faster access, and or they are safer than single disks. It can be both faster and more secure, or only faster or only more secure. Data is distributed among those disks. Not in all solutions, but in most of them, information is divided into stripes, portions of data, larger than a sector. The right solutions have numbers. Number of right defines the solution. Right zero is splitting data between disks. What we achieve? Faster access. Because, as I showed you, reading or writing of data is preceded by some operations like moving heads, activating heads. So, if we read some sequence of data, we can read data from stripe 0. At the same time, this disk activates heads, this disk moves heads, so the transmissions overlap in time. If those disks have individual subbuses, we can even order transmissions in parallel on subbuses. On a single bus, of course, not. But if we have subbuses, we can even read data in parallel or write data in parallel. Of course, if the disk has mean time before failure X hours, it is typically provided in hours. Luckily, in thousands of hours, not in single hours. Then N disks has the error rate N times higher. Write one is mirror. We write the same data on two disks. So if we have stripe 0, it is repeated on two disks, stripe 1, 2, and so on. The rule is that it is just mirror, the data are repeated. We have 2 bits 0, 0 on stripe 0, so 2 zeros on stripe 0 on the second disk. Exactly the same. It is a very safe solution. However, it is costly because all data must be duplicated. It's good for reliability. and it's costly solution. And there is one danger when we have automatic error correction. I used to have such a symptom in past that the right controller discovers difference between disks, but identifies erroneous disk wrongly and moves spoiled data over correct data. I had such a problem. It took more than a year to identify this problem. What happens that data are corrupted? Okay. It could be done in n-mode redundancy. If we have 3 disks, we can vote. But such a solution is not used for APT because it's too expensive. Maybe in space devices, I don't know. It's write 1. And we can mix those solutions. Typical desktop controllers in PCs, modern desktop controllers, are able to arrange write 0, 1, 1 plus 0, or 0 plus 1. When you find a solution that is write 10, it's not 10, it's 1 plus 0. Those writes arrangements are up to 6. So there is no write 10. Write 0 plus 1 is that we first disseminate stripes to several disks. Then we organize 2 farms of disks, and we arrange a mirror of 1 farm on the second farm. 1 plus 0 is reverse. We first duplicate every disk, then we arrange a farm of such duplicated disks. I use such solution in my desktop. I have 4 disks. In 2 writes 1, then I switched on write 0 for speeding up and enlarging space, because I have single logical disk on 2 mirrored physical disks. Write 2 is not used. Why? Because in write 2, which is very safe, in write 2, we synchronize the spinning velocity of disks. So we have a beginning of track signal at the same moment in time for all disks. They are synchronized. It's very expensive. So such write is not used nowadays. It's very safe because it uses correction code. Correction code, for example, Hamming code, discovers an error and appoints the number of bits that is corrupted. And we have for every nibble, this is nibble, D0, D0, D1, D2, D3. If a bit is corrupted, those control disks appoint number of bits that is corrupted, and we can reverse this bit to restore correct information. This is the way the Hamming code works. It is costly, but less than mirror. Here we have 3 control disks because we have 4 bits. So it is 2 to the power of 2. For 8 bits, so complete byte, we need only 1 control disk more. Because every control disk doubles number of bits that we can control. Write 3. Similar to write 2, but correction code is replaced by detection code. We control data by parity bit. Okay, we can say that if data is corrupted, we know that it is corrupted if 1 bit is corrupted. Because if there are 2 bits corrupted, parity does not help. So if 1 bit is corrupted, we know that the entire data is corrupted, but we don't know the number of bits that is wrong. In Hamming code, we know. Here we don't know. However, typically, if the disk fails, we know which one fails. Typically, not always. For example, if the disk does not respond, we know which one is corrupted. Modern arrays are hot flag. That means that we can just remove the disk without switching power supply off, replace with new one, and the array will restore the data. How parity works. For example, we have bits 0010 in this nibble. And if the parity is even, the parity bit will be 1. Because we need to have even number of ones in every nibble. This has even number of ones, so parity is 0. So for example, if this disk is switched off, replaced by a new one, filled entirely with zeros, we can observe here we have 0, 0, 1, 0. Parity is 1. It means that we have even number of ones, so we leave this bit 0. Here we have 0, 0, 1, 1, 1, 0. If we replace this, we have 0. Having parity 0, we have odd number of zeros, so we know that this bit should be negated. Such a way we can restore data on a disk. But forget about this. We do not use write 3 because of synchronization of spinning velocity of this. Write 4. Write 4 is similar to 3, but instead of parity bits, we have parity stripes. We have stripe 0, 1, 2, 3. For every bit in 4 stripes, in this example for 4, it could differ. We have in parity stripe bit, we have parity bit. For this 0, 0, 1, 1, so parity 0. For every set of stripes, we have parity. Parity stripe, not parity bit. This solution does not require synchronizing the spinning of disks. And typically it's hot plug in commercial writes. However, assume that we replace some data in stripe-free. Naive solution is read all those stripes, 0, 1, 2, 3, recalculate parity, and write it down to parity disk. But it could be made more clever because we can take the old version of stripe-free and new version of stripe-free, and we can negate all bits that differ in old and new version of stripe-free. It's the same. If the bit changed, parity must change. If a bit is the same, parity remains the same. However, in this solution, parity disk is overloaded because every change in every stripe requires write to this stripe and to parity. So this is heavy load. This disk is heavy loaded. The solution is write 5. It differs only in fact that the parity stripes are disseminated over all disks. We have also write 6 that does not differ from write 5, only the parity stripe is duplicated. So if we lose parity, we have second parity. We can check if one parity does not give given parity. For example, parity is odd and given bit gives even parity. We know that something is corrupted, and we take the second parity stripe and check if it provides correct parity value. So we duplicate parity stripes. So in typical write solutions, in desktop computers, we use write 0, 1, 1 plus 0, 0 plus 1. In server solutions, commercial solutions, we use write 5 or 6. Okay. So we switch to the next slide set. It is higher level of information arrangement. It is file system or massive memory. Mass storage. My slides generally follow Tannenbaum book. And some solutions are not used anymore. This is an example of solution that is seldom used, is file structure. In 60s, last century, in 50s, first disks were produced. So first file systems were built, very simple. And for user convenience, several arrangements of files were applied. For example, serial files and indexed files. In indexed files, we had the file divided to records, every record divided to fields with key fields, and built tree of index. Over years, more and more versions of file arrangement were elaborated, and users did not know which organization to use. For example, in 70s, in IBM 370 machines with OS system, there were more than 10 file arrangements, and there was a handbook over 200 pages about the arrangement. And I'm afraid that only IBM engineers read this book, that no user read this book carefully enough to choose correct file arrangement. Oh, of course, IBM engineers offered help for this issue, charging $1,000 per day. So they were lucky about this fact. And this was one of the reasons that engineers from Bell Labs they sent set of their wishes for operating system they used on PDP-11, but the producer DEC company ignored those needs. Oh, it's typical. Computer engineers are not loved in companies they work, because they say, I say you, it must be done such a way, and don't ask why. So they were nervous in Bell Labs, and someday two people from Bell Labs, Ritchie and Thompson, built Unix. In this system, they realized all their wishes for operating system, including files, because, as I told you, people don't want to read complicated books to read how they can organize their data on the disk. They just want simple solutions. So they decided a file is a sequence of bytes, not more. If someone needs records, fields, key fields, let him do that. On the top of operating system in software that nowadays is called middleware. For example, we have relational database management systems over operating systems. By the way, the disk arrangement offered by operating systems is not very good for relational databases. Oracle can store data in files, but the hint from Oracle is give us the entire partition of your disk and we will arrange data in our manner. It must be more safe, faster, easier, everything better. Okay. But there are some operating systems that offer such arrangement of data. That the files are not just sequences of bytes, they have internal structure, and they have some means to speed up access to given data. So we will take them into account, not only simple files that are series of bytes. Okay. What does the operating system do in management of the storage? It manages all data on the disk and allows to input data to programs as input data and store the results as output data and keep the data in form that is resistant to errors, malfunctions, concurrent usage of people, some dangerous situations. So operating system offers exclusive access method. We cannot access the disk on file level by one program and on sector level for other programs. Because it's dangerous. Because operating system cannot guarantee the correctness of logical data on the disk if raw access to disk is offered to some programs. So, except some tool programs run in privileged mode, all users see the same structure and can use the disks or other devices only in that manner. And in result, operating system guarantees correctness and safety to some level, of course. It optimizes access to be easiest and more safe and fastest. Of course, those requirements contradict somehow. So it is a trade-off between them. The access methods meet user requirements. Nowadays, when we have independent software producers, we choose the best operating system for us. But formerly, operating system was delivered together with computer. So user had little influence on the manner of access to the devices. That's why producer-independent operating systems were established, like Unix, for example. Minimization of data loss in case of errors. Special structures are prepared to restore data in case of problems. Sharing data for many users, especially concurrent access to file. And covering possibly largest set of devices that can store data, like disks, electronic disks, optical disks, CD-ROMs, DVD-ROMs, flash disks. On every device, we see similar structure. Of course, technically, access depends on the kind of device, but it is hidden in this multi-level driver structure in operating system. And we see all those devices sharing common structure. Requirements for user and programmer is creating and modifying records in byte-based files. The records are single bytes. Controlled access to other users' data, so it is access rights. I can allow or not other users to access my files. Is protect the files from myself. I can mark a file read-only. Read-only is a file that I cannot write and I cannot remove from the disk. So even if I remove all files from the directory, read-only files remain. So I would be safe from myself. Changing the structure of private data. For example, if we have file structure, changing the structure of one type to another type. Moving data in hierarchy, changing the owner of data. Data restoring in case of the match of some organizational data. If the file is erased, cannot help. If the manner of accessing the file is corrupted, we can do some actions to restore. Referring to data by symbolic name. So my file is not third file in fifth directory. I can give a name to the file, name to the directory, just like in internet. Okay, IP address physical is 4 or 6 bytes. But we do not use this addressing. We use PW-EDU-PL for our university. Operating system is the end of our today's lecture. Thank you and see you next week.